said, hey, you, let's do some DIFFERENTIal. If something's looking blurry, then we'll bring it into view. I said, hey, you.
Check it out.
Welcome. Let's do some DIFFERENTIal. In this video, we're going to look at power series solutions and finding the solution to a linear system using matrix methods. Let's get started. Say we want to solve this differential equation using power series methods. In particular, we want to look at a power series centered at x naught is equal to 0. Now note that x naught equal to 0 is an ordinary point. The function in front of y double prime is just 1, and actually there's no point that can be substituted into this function 1 because it's just a constant function. And since that's the case, we can't possibly get 0 here, meaning there are no singular points, and in particular, 0 is an ordinary point. What that means is we don't have to use the Frobenius theorem. We can just use a standard power series for our solution type. Such a solution type will look like this, where we have unknown constants, a sub n, and then we take x minus the point. Of course, since the x naught is equal to 0, we have this here. And now if we take the derivatives, we get first derivative and second derivative like so. What we want to do is assemble the 0th derivative and the second derivative together. If we take x squared times y, what we get is this, namely where we have x squared, so that will increase the power by 2. Now note what we've done here is adjust the starting index, which correspondingly adjusts all the inner indices. The n becomes n minus 2, the n plus 2 becomes n. The reason we do that is we would like always to have x to the n here. That way, we can combine terms more easily when we have multiple series in a row. Now, in the differential equation, we'll have just y double prime. So we list that just for reference. And in particular, we again change the index so that what we have is x to the n. Notice in both of these cases, we have x to the n. Now, it actually doesn't really matter if it's x to the n or x to the n plus 1. It just matters that it's always the same here. So if there's x to the n here, we'd like x to the n here. If there was x to the n plus 1 here, we would also want x to the n plus 1 here as well, just as long as it's the same between all the different series. But x to the n is kind of a good base one to shoot for. Now let's assemble these series into the differential equation. We'll take our differential equation and we'll color it to make it a little easier to follow the terms. Y double prime will color cyan, and x squared y will color yellow. Now substituting in the series versions, this is going to be equal to 0 still, but we have the cyan being this series and the yellow being this series. Now from there, what we want to do is combine terms using the index. So first, we'll look at all the cases where we have x to the 0. Since this yellow series starts at n is equal to 2 and we have x to the n, this will have x squared, x cubed, x to the 4th, to the 5th, and so on, but it won't have any x to the 0 term. It also won't have any x to the first term. But this one, since n here in this series starts out at 0, we will have a x to the 0 term. Now again, we have this all equal to 0, but there's a n is equal to 0 term where x to the 0 is 1, we have n is 0, so we have a sub 0 plus 2, or a2, and then we substitute n is equal to 0 here. The same is true for n is equal to 1. This series does not have that, only this one does, so we'll write the n equals 1 term. And then finally, once we hit n is equal to 2, both of these series have n is equal to 2, so we can combine their coefficients all together. And if we do, we get this. So notice we've combined the coefficients. Since these sides need to be equal, we notice that this term has an x, these terms all have x squared, x cubed, x to the 4th, and so on. We want to match up like terms on the left-hand side with like terms on the right-hand side. Since the only constant on the right-hand side is 0, that must mean that this is equal to 0, and hence a2 is 0. Similarly, we can think on the right-hand side of there being 0 times x, which makes this coefficient equal to 0. And hence, a3 is equal to 0. And the same goes for every x squared, x cubed, x to the fourth, and so on, this coefficient should be 0. This will actually give us a recurrence relation. Here we can directly find out what A2 and A3 are. To summarize, by setting the left-hand side terms equal to the same terms on the right-hand side, that is like terms, we get A2 is equal to 0, we get A3 is equal to 0, and then we get a recurrence relation. And what this recurrence relation says is the A sub n plus second term is just a multiple of the A n minus 2 coefficient. Therefore, suppose you let n be equal to 2 to start with, you'll have actually A0, but then since n is equal to 2, you'll have A4. So A4 is just a multiple of A0. If you had n is equal to 3, you would have A5 as a multiple of A1, and so on and so forth. If we say that A naught or A sub 0 is y of 0, which it is, always, that value will tell us what A4 is. That value will then tell us what A8 is, and then that will tell us what A12 is, and so on. And that's because of this recurrence relation. So we have y prime of 0, which is A1, gives us A5, gives us A9. Then we have that A2, which we said is 0, gives us A6, A10. And because of this recurrence relation, where A6 is just a multiple of A2, any multiple of 0 will just be 0, and so on. So all the terms given in this string are going to be 0. And that'll be the same case for A3, A7, A11, and so on. These terms here will all be based on what A naught is. That is y of 0. So if you know y of 0, you'll know all of these. Just scaling by the appropriate number. Same thing, y prime of 0. That'll tell you what all of these are. If we assemble that information, making note of this recurrence relation, which I now note was missing a negative sign, what we will have is this string here. We have y of 0, 1/3 times 1/4 y of 0, and so on and so forth. So it can all be written in terms of y of 0. Same thing for y prime of 0. And I want to make a note, I missed a negative sign previously. That should be here. That'll give us this series. And I want to note that I missed a negative sign, which will change a sign of a few of these terms, namely these here. The important thing to note in this case is how we can determine the whole series and any term in the series simply by knowing y of 0 and y prime of 0. Now let's look at a second example. This example will go through relatively quickly because it's pretty similar to the first one, but just so you can see another example for reference. Here we have this differential equation, and we want to solve it using power series methods about this point. Just like before, we note that it's an ordinary point because substituting it into this function, which is just the constant function, will not give it 0. That is, we can now take a power series solution to be of this form, x minus x naught. X naught is 0, so we get this. Take the derivative, and then the second derivative. Then multiply y by 4x, because that's what we have here. And then rewrite, where at this point we've changed the starting indices so that this one starts at 1, and we have x to the n. This one starts at 0, we have x to the n. And again, we want these to be the same. It'll make it easier for combining like terms. Writing our differential equation like this and highlighting with color, we substitute in the given series. And then if we combine like terms, noticing that n equal to 0, only this series has that. But then after that, n equals 1 and above, both of the series will have terms with that x to the first power. We get the n equals 0 term, and then the series with the general form for n is greater than or equal to 1. And now, since we're going to equate the left side to the right side, there are no constants over here except for 0. That means that this expression must be 0, and therefore a2 is equal to 0. And then likewise, every single one of these coefficients must be 0. Taking that and rewriting it, we get this here. This means we can find successive constants or coefficients from previous ones. That's what the recursion means. You get new ones from previous ones. And this will give us a recurrence chain. So we have a naught, which is just y of 0. That will tell us what a3 is, which will tell us what a6 is, and a9. Y prime of 0 will tell us what a1 is, what a4 is, a7, and so on. And a2, which we do know to be 0 here, will tell us what a5 is, a8, and in particular, all of these are going to be equal to 0. Rewriting, since our series started out like this, and we're able to now determine what some of these coefficients are, we have this series. Now let's look at some of the properties of a matrix to review those so that we can solve linear systems using matrix methods. Given a matrix A, like so, there are two important properties of this matrix that are useful to track: the trace and the determinant. Now these are defined for any square matrix, but we'll in particular look at 2x2 matrices here, just because that's what we'll focus on as far as solving actual systems. But note, this would work for systems with 3 variables, 3 equations, 3-dimensional matrices, and so on. So we have the trace and we have the determinant. The trace is simply the sum of a plus d, or the sum on the main diagonal. The determinant is the main diagonal minus the off diagonal product. And this actually has a geometric meaning. It's the area formed by the parallelogram between these as vectors in R2. A little reminder that I like to give myself, and you may find useful, is that the trace uses one diagonal, the main one, and the determinant uses the main and the off diagonal. Now these are going to be particularly useful when we're trying to find eigenvalues and eigenvectors for 2x2 matrices. We say an eigenvector of an m by n matrix A is an n-dimensional vector such that this equation holds. If you multiply the matrix times the vector, what you get is just a scalar multiple of the vector, where this lambda is just some real number. This value is called an eigenvalue, and it's always associated to an eigenvector. So you can really think of these as coming in pairs, an eigenvector with an eigenvalue. Now, eigenvectors are not unique. You can have an eigenvector and then have a scalar multiple of it, still be an eigenvector. But we consider that class of eigenvectors where they're all associated to a particular eigenvalue. We kind of consider them to be the same thing. The eigenvalues are values that don't change. If you have 2 of them, it's 2 specific numbers and that's it. Whereas eigenvectors, if you have an eigenvector associated to a particular eigenvalue, you may have multiple versions of that eigenvector, but they're just going to be scalar multiples. Now, what are the ways that we find eigenvalues and eigenvectors? There's 2 methods that we'll look at in the case of 2x2 matrices or 2x2 linear systems. The first is using the inverse matrix theorem, which is a absolutely massive theorem that links all these equivalent conditions for a matrix to be invertible, or the determinant of a certain matrix system to be 0. It says something like 20 different properties are all the same. So it's a big theorem in the sense that it says many different things are equivalent. But for us, we only need to know that 2 things in particular are equivalent. Besides the inverse matrix theorem, you can also use the trace and determinant. But note, this will really only be helpful when we have a 2x2 system, because if you have a 3x3 system and you need to find 3 eigenvalues, since trace and determinant are only 2 different things, we'll only have 2 equations. So if we have 3 unknowns and only 2 equations, we won't be able to fully solve for each one. Let's look at the first method real quick. Essentially what we'll do is we'll start with this property, that if V is an eigenvector and lambda is an eigenvalue, we have this fact. Then, rewriting a little bit, we can say this. Now, from the inverse matrix theorem, what we can say is this equation being equal to 0 will only occur if this is equal to 0, so long as this thing itself is not 0. So if this is a non-zero vector, and it should be taken to mean that it's not, then what we get is the determinant of this matrix A minus lambda I, that thing is equal to 0. And that's again by the inverse matrix theorem. The other way that we can find the eigenvalues is using the trace and determinant. These following facts extend to cases of 3x3, 4x4, and so on. If you have the trace, that's going to be equal to the sum of the eigenvalues. Notice that's normally the sum of the main diagonal entries, which are not equivalent always to the eigenvalues. In fact, most of the time they're different. But if you sum up the main diagonal entries or you sum up the eigenvalues, both cases they'll give you the trace. Part of the reason that trace is so important. Alternatively, the determinant is going to be just a product of all the eigenvalues. So again, if we're looking at an n by n matrix, the trace is equal to the sum of the eigenvalues, and the determinant is equal to the product of the eigenvalues. But here we have just two equations, the trace and the determinant. If we have more than two unknowns, since we only have two equations, that won't allow us to solve for all the different unknowns. But in the 2x2 case, two equations, two unknowns, we'll be able to solve for both of the eigenvalues. Now let's look at an actual example and just go through the whole process. Say we have the linear system dx dt is equal to 2x plus y and dy dt is equal to just y. The associated matrix equation to this system looks like this. Writing this is the same thing as writing this in a matrix form. Where note, if you were to multiply this matrix times this matrix, where I'm calling this a matrix, but it's just a 2x1 matrix, times this 2x2 matrix, then you would get this one. And notice we're taking xy, where x is a function of t and so is y. And then here we're taking xy prime. That represents the derivative of x with respect to t and the derivative of y with respect to t. And then the matrix here just gives us the values 2, 1, 0, 1, 2, 1, 0, 1. We look at this matrix A and we compute the determinant and the trace. Those give us correspondingly 3 for the trace and 2 for the determinant. Now what we said is the trace, besides this computation we do with the actual values in the matrix, remember the first way we looked at it is to just take the values of the matrix and do the sum. So we take 2 plus 1 to get 3, and then we take 2 times 1 minus 0 times 1, which is 2. That's going to be alternatively equal to the sum of the eigenvalues for the trace, the product of the eigenvalues for the determinant. The values that satisfy this are lambda 1 is equal to 1 and lambda 2 is equal to 2. Or vice versa, we could have said lambda 1 is equal to 2 and lambda 2 is equal to 1, doesn't matter. The fact is we get that one of them is 1 and one of them is 2. Now you might think that we should always get integers for the eigenvalues, but that's not necessarily the case. They can be rational numbers, they can be irrational numbers. They don't have to be integers. We're just going to pick problems where they are, or they're relatively simple rational numbers, just to make it a little easier to compute. But in general, they certainly do not have to be integers or even rational numbers. Now what we'll do is for each one of these eigenvalues, we'll find an associated eigenvector, or a class of vectors, if you will. If we start with lambda 1, what we're doing is we're looking for some vector xy such that what we get is the matrix times the vector is just a multiple of that vector. And in particular, since we're looking at lambda 1 is equal to 1, we want it to be 1 times the vector. So just the vector itself. If we do the multiplication through on the left, we end up with this, setting it equal to on the right. We get two equations, 2x plus y is equal to x, and then we get y is equal to y. That shows us that x is equal to negative y. If we substitute that in, what we get is this here. We take xy, we said that x is equal to negative y, so we replace it. We factor out the y, which is common to both of these rows, and then we're left with the vector negative 1, 1. Now notice we could have alternatively substituted negative x is equal to y, and so on. There's flexibility. We could have also had the vector 1, negative 1. That also would have worked. We could have also had the vector, say, 2, negative 2. Any multiple of negative 1, 1, or any multiple of 1, negative 1, so on, is going to be an eigenvector associated to this eigenvalue. We could have even had, say, negative pi if we wanted, as long as it's just a scalar multiple of one of them. Likewise, with lambda 2 is equal to 2, we're looking for some vector xy such that this equation is satisfied. Multiplying it out, what we get is this set of equations here, which tell us that y is equal to 0. Now we substitute in y is equal to 0 into our original vector, and we get this eigenvector here, where again, we could have had a variety of other vectors such as 3, 0 or negative 17, 0. Usually, though, you want to pick kind of the simplest one, and I think 1, 0 is about as simple as it could get. So let's take actually these two vectors. Let's take 1, negative 1, and then 1, 0, and those will be our eigenvectors. And now to finish this problem off, we started with this linear system. We came up with these two eigenvalues. We came up with associated eigenvectors, where we could have had different representatives, but we chose what we thought were maybe the simplest ones in each case. So we had 1, negative 1, and then we had 1, 0. Now we assemble these in the following way. The eigenvalue gives us the value in the exponent spot here. So we have eigenvalue of 1 times t, correspondingly 2 here, so it's 2 times t. And then we multiply the associated eigenvector times that exponential. So we have e to the 1t, eigenvalue 1, times its associated eigenvector here. And then same thing, we have eigenvalue 2t, and multiply by the associated eigenvector. Now, all these vectors do is they give us essentially two levels of equations. They give us a top and bottom level. So we take C1, multiply it times both of these values, and then multiply this times both of these values, and same thing here. So we get C1 times 1 e to the t, that's this, then plus C2 times 1 e to the 2t, that's this. Then for the bottom row, we get C1 times negative 1 times e to the t, that's this, and then the other part gives us 0. I hope you found this video useful. We'll see you in the next video. To view the next video in this series, click the link on the right. To view the last video in this series, click the link on the left. If you want to learn more about me, the nerd who's making these videos, visit the website below. And as always, have a good day.